Hello everybody, today we are going to solve the famous J Advanced 2016 question, which is said to be the hardest question of J Advanced ever. This is of rotational motion. This question is of rotational motion, and today we are going to try to solve it, and I'm going to solve it and try to explain it to you as best as I can. Okay, so I'm just going to read out the question once so that you get a more clarity. It's very long to write, you may be knowing. So, two thin circular discs of mass m and 4m having radii a and 2a respectively are rigidly fixed. So, they are rigidly fixed by a massless rigid rod of L equals to root 24a. Okay, I have made the diagram through the centers. Okay, so the centers, the distance between the centers is L equals to root 24a. This assembly is laid on a firm and flat surface and set rolling without slipping on the surface so that the angular speed about the axis of the rod is omega. So this is the axis of the rod and angular speed about this is omega, right? Angular speed about this is like this omega. The axis is like this, so it is omega like this. Okay? The angular momentum of the entire assembly about the point O. So this is the point O. So the angular momentum about this point O is given to be L. Okay. So we'll have to find this L angular momentum about the point O. Okay. Which of the following statements is or are true? The first option is the center of mass of the assembly rotates about the z-axis with an angular speed of omega by 5. So we need to tell that the center of mass, let's say this, rotates by what angular speed about this z-axis. So about this z-axis, the center of mass rotates by what angular speed. So about its own axis, it is omega. But about the z-axis, what is the angular speed of the center of mass? That we need to find out. Okay. So L is equal to root 24a. This is a right angle triangle. This is a right angle triangle. So by simple math, let's say this is x. So x square equals to 24a square plus a square, x equals to 5a. So this is 5a. Similarly, for this bigger triangle over here, we have 2a square equals to 2l, plus 2l square equals to, let's say, y square. Okay. So 2a square, 4a square plus 2l square, 4 into 24a square. 4 into 24, 48 in 96. 96a square equals to y square. 100a square, so 10a. 10a equals to y. So this remaining length over here becomes 5a. Right? So this remaining length over here from this point to this point is 5a, and from this O to this point is also 5a. Okay, that we have figured out. Now one more thing we see over here is this angle. This is playing a crucial role over here. So this angle, so the sign of this angle we can directly see is a by 5a, as 5a is the hypotenuse of this triangle. So a by 5a is sine theta. So sine theta is basically 1 by 5. Sine theta equals to 1 by 5, and cos theta also we can write root 24 by 5. Why? Because it will be L by 5a. L is root 24a. Okay. I hope I read out the question that this whole assembly is rolling and without slipping, right? I think I read it that the whole assembly is rolling with an angular speed of omega about its axis. So it will be going like, if this is the marker, so it will be going like this. It will be rolling like this. Okay, so it will not be plane motion. It will be like the assembly is tilted like this and it will go like this. Okay, I hope you understand. It will go like this. Okay, try to picturize it, you'll understand better. Okay, So now about talking about the center of mass. Let's find the center of mass. We'll use it later also. So let's just find the center of mass. Let's say this is point 0, and this is point L0, right? So the center of mass will be m into 0 plus 4m into L upon 5m. So that will be equals to 4 by 5L. So at 4 by 5L, away from the center, 4 by 5L, the center of mass will be located. Okay. So from origin, from the point O, it is 9 by 5L away. So the distance of center of mass from the origin is 9 by 5L. Okay. Cool. Now we found the point where the center of mass is. Now important thing over here is that this disc, and this rod of length L, this is a rod. So this rod of length L, are a rigid body. So the angular velocity of this disc about the z-axis, and like the center of mass of this disc about the z-axis, center of mass of this disc about the z-axis, and every point on this rod about the z-axis will have the same angular velocity about the z-axis. Why? Because this is a rigid body, right? So like if this whole body is there, this is one body, then this point, all will have equal angular velocity about the z-axis. Even though their linear velocity will be different or can be different, the angular velocity will always remain the same, right? So what is angular velocity basically? It's linear velocity upon the radius. So V upon R is basically omega, right? So what we need to do, we just need to find the linear velocity of this point and then divide it by 5a, because that's the distance of this center of mass of this disk from the origin, right? From the z-axis, sorry. So it is 5a units away from the z-axis. So that's why whatever its linear velocity is, or wherever it's going, that divided by 5a will give its angular velocity. So what is linear velocity? A into omega. We know that linear velocity is equal to r omega. R we have a, and it is going with omega angular velocity about its own axis. So v equals to a omega, right? And r we have given over here v by r. For v by r we have 5a, right? So it's from the z-axis, it is 5a units away. So a omega upon 5a, that will give us omega by 5, right? So this point has angular velocity omega by 5 about the z-axis. Let's check for this point also over here. So this is 10a units away, and its linear velocity is 2a omega. So 2a omega upon 10a omega by 5. Okay. So every point in this assembly will have a angular velocity of omega by 5 about the z-axis. So obviously the center of mass will also have an angular velocity of omega by 5 about the z-axis. Okay. So that option is correct. Okay. I hope you understood. Let's move on to the next part. Okay. So for the next part, so they are asking about the z component of L, basically the angular momentum of the whole assembly, the magnitude of angular momentum of the assembly about its center of mass. So angular momentum about its center of mass, and magnitude of angular momentum of center of mass of the assembly about point O. Okay, so it is asking about the angular momentum of center of mass about point O. Okay, it is asking about the angular momentum of assembly about the center of mass and magnitude of z component of L. So let's go with this part, the magnitude of angular momentum of center of mass of the assembly about the point O. So they are saying that this center of mass has what angular momentum about this point O, right? So they are saying in the option they are claiming that it is 81 ma square omega. That is what they are saying is the angular momentum of the center of mass about O. Okay, let's see if that's true. Now how are we going to do this? Okay. So we know it's, as this is a point mass, we are going to use the formula R cross P, right? This will be the angular momentum, that will be R cross P. Now R is 9L by 5, 4L by 5 plus L, that is 9L by 5 cross P. P is mass into velocity. Mass is given to be 5m. Now what we have to do, we just have to find the velocity of this point mass or the center of mass. So for that we know that it is rotating with like omega, right? So it is rotating with omega about its own axis. So its linear velocity we know is r omega, right? This point's linear velocity we know is r omega. So we just need to find this length over here that we have, right? So like for this point, what was the linear velocity? The linear velocity was 2a omega, right? And why is it 2a omega exactly? I forgot to tell you why it is 2a omega. That is because this is rolling, purely rolling, right? So basically for the lowest point, the velocity, so basically for the lowest point, the net velocity has to be 0. For pure rolling, the lowest point, this point should have net velocity 0. So V has to be equals to r omega, right? The lowest point. So over here also V has to be equals to r omega, right? So similarly for every point, V is basically r omega. Okay, as it is rolling. So over here also we had to say V equals to r omega. Over here also we had to say V equals to r omega. So over here for this point also V will be equals to r omega. So now what is this distance over here? We already know sine theta is equals to 1 by 5 and cos theta. Okay, so cos theta, no, what will work? I think okay, let's this is 9L by 5, right? This length is 9L by 5, and so cos theta, so root 24 by 5 equals to 9L by 5, that is base, upon hypotenuse. So hypotenuse h, root 24 by 9L, sorry, 9L by root 24 equals to h. So L is root 24a, h equals to 9a. So this is 9a units away. This over here is 9a units away from the origin. 9a. Okay. So now that we have found the hypotenuse, using sine theta, 1 by 5 equals to x upon 9a. 9a by 5 equals to x. So this is 9a by 5. This over here, this distance is 9a by 5. Okay. So we have found this distance 9a by 5. Now what we know is V equals to r omega. So V equals to 9a by 5 omega, right? So let me erase all of this. V equals to r omega. Okay, so V equals to R omega, V equals to 9A by 5 omega. So over here, R cross P, R cross MV, M over here we know, and V is 9A by 5 omega. Okay, now 5 gone, and L we can write as root 24A, right? So this will be 81 M A square omega root 24 by 5. This is what we are getting as the this is what we have calculated, the angular momentum of center of mass about the point O. So this is the angular momentum of the center of mass about this point O. It is 81 ma square omega upon into root 24 upon 5. But the option said that it is 81 ma square omega. If you see, root 24 is very close to 5, right? Root 24 is very close to 5, but it is not exactly, this is not exactly equal to 81 ma square omega. It is very close to it, but it is not exactly equal to that. So this option is wrong. Okay, this option is wrong. The angular momentum of the center of mass of the assembly about the point O is not 81 ma square omega. Okay. Okay, coming on to the next part, the magnitude of angular momentum of the assembly about its center of mass is 17 ma square omega by 2. That is what they are asking. The magnitude of angular momentum of the assembly about the center of mass. So about this point, they are asking the angular momentum. Okay. So they are saying that it is 17 ma square omega by 2. That's what they are saying. Okay, let's check if that's the case. Let's see, let's calculate that. So in CRTM, we know that the angular momentum is I omega plus R cross P, right? This is the angular momentum in CRTM. But if you see, the center of mass is also moving. If you see, the center of mass is also moving, right? Center of mass is also going like this, right? So relative to the center of mass, if you sit on the center of mass and look at these two discs, for you they are just rotating. If you sit on this and just look at the two discs, they are just rotating. They're not actually doing any translation motion for you, relative to you, because you are moving along them, right? So like as this disc moves like this and this disc moves like this, similarly the center of mass has also moved some distance with them. Okay, so for the center of mass, the what you say, the angular momentum will be just I omega, because the center of mass just sees them rotating. It does not see them moving or performing translation motion, right? Translation motion when happens, then we use R cross P, right? But for the center of mass, the discs are just rotating, so it is I omega, right? It is I omega. So we can erase all of this. This that we calculated was the angular momentum of center of mass about of the assembly about the point about the point O. Okay. The interesting thing is this angular momentum. What is its direction? What is the direction of this angular momentum of the center of mass? Because angular momentum of center of mass is essentially giving us like the angular momentum, the movement. So basically angular momentum, how can I explain this? Angular momentum is R cross P plus I omega, right? So for this point O, from this point O, what will be the total angular momentum? It will be the sum of basically angular momentum of this disc rotating and then this disc moving like this. right? So this disc moving like this will have some angular momentum, and these discs rotating like this will have some angular momentum. So adding those two, the vector sum of the two will give us the total angular momentum about the point O, that is L, right? I hope you understood. Basically there are two angular momentums. If you see, one is the rotating of this disc and its direction is like this. Oh my god, my drawing. Like this. This is the direction of the angular momentum of these discs rotating. How? If you see, how can I explain this? If there is this disc rotating like this, so its angular momentum direction is like this, L, right? Or what is it? Yeah, L. It's rotating like this, L, right? Similarly with for the direction of omega, what is it? Let's do it like that. The direction of omega, what is it? It's like this, right? If a disc is rotating like this, the direction of omega is like this, right? And then angular momentum will also have the direction of the angular velocity, right? If the angular velocity has direction upwards, the angular momentum will also have a direction upwards, right? Because it is basically I into omega, right? So L is also going upwards like this. So for here, if these discs are rotating like this, so angular momentum will be like this. So let's say this is L1. This L1 is due to the rotation of the disc. Now there's another angular momentum that we calculated, and that is movement of this whole system like this, right? So it will go, it won't be around the z axis. It is like it has its own axis, right? This is its own axis. So it is going like this. Like, how can I explain? Try to visualize this. If you like, instead of this tilted axis, if you just straighten this out and try to visualize, it's like this right now. If you straighten this out and then visualize, and if the whole thing is going like this, so if it was like this and this whole thing was rotating about this, right, then the angular momentum will be like this. But now this whole thing is tilted, so the angular momentum will go like this, right? If it was like this, then let me just erase this, so I think I can explain this to you, because understanding this is very important. This is the whole crux of the question that you need to understand. This angular momentum of center of mass we found out to be 81 ma square omega root 24 by 5. Okay. Now if this whole assembly was not tilted, it was like this, right? So this whole assembly was like this, right? So the rotation of this whole assembly, if it would have rotated about this point, then the angular momentum would have direction like this, right? Now if we just tilt this whole thing, then we'll get something like this, right? Just tilt this whole thing, so you'll get the direction of angular momentum to be this. So the direction of angular momentum becomes this, perpendicular to the axis of rotation. Let's say L2. Okay, so this whole, when it is rotating about this point O, its angular momentum is L2, and funnily its value is 81 ma square omega root 24 by 5. Why? Because the center of mass has that angular momentum about O, right? So if you would have taken this individually, or you have just directly taken the center of mass angular momentum about O, it is coming out to be 81 ma square omega root 24 by 5. If you would have taken that individually also, the same result would have come. Why? Because then you would have taken this to be L to be the distance in R cross P, L to be the distance, right? So it would be L into mass is M, velocity is A omega, right? It is A omega, I believe, yes, plus R cross P, so R over here 2L cross P, M 4M, 4M into velocity 2A omega. So L you can write as root 24A, so you will get root 24 MA square omega plus 2L, so 2 root 24A, 8 2A, 2 into 2 into 2 4 16 root 24 no, this won't give the answer to you. M 2A omega and no, this won't give the answer to you. Okay, I'm missing something over here, but basically the center of mass, we took the center of mass, and then basically about O, its angular momentum came out to be this, and that's the angular momentum of whole assembly. About this component of the angular momentum of the whole assembly is 81 ma square omega into root 24 by 5. Okay, so this component has this value. Now we are trying to find the value of this component, because about the center of mass, the angular momentum for the center of mass, what it sees is these two disks rotating, right? What the center of mass sees is these two disks rotating, right? The center of mass sees these two disks rotating for it. So for the center of mass, it will basically be the sum of I omega for this plus I omega. So whatever the moment of inertia of this is into omega plus moment of inertia of this into omega, right? So this, what I tried to do over here was trying to find this component of the angular momentum about O by taking these individually, but that's not giving us the correct result over here. Can't figure out why. So if anyone watching this video knows what mistake I'm making here, please let me know. That will be really helpful, or I'll research it up after this video, but that's not important. The core idea was about O, this component will basically be the angular momentum of center of mass, right, of O, because then center of mass is a point mass, so it won't be like rotating like this, right? It's a point mass, so it won't be rotating like this. It will have only an angular momentum of it going like this, right? I'm trying to explain the level best that I can, so I don't know if you guys are able to understand, but I think I'm explaining well according to this question. So this over here for the center of mass, it will basically I omega plus I omega. So let's speed things up. M r square by 2 4m. Let me just change the marker. 4m m r square 4a square, or m r square m r square divided by 2 into omega, plus m r square divided by 2 into omega. So 4m 16 ma square omega by 2, 17 ma square omega by 2. So this is the value of angular momentum of this system about the center of mass. Why is this? Why are we only taking the rotation of the disks when considering the angular momentum about the center of mass, because the center of mass is going with them when it is rotating about point O, it is going with them. So that R cross P component we won't take about the center of mass. For the center of mass, these two disks are stationary and are rotating, right? So that rotating angular momentum we took. Okay, so that is coming out to be 17 ma square omega by 2. So this option will be ticked because that was what was given in the options, 17 ma square omega by 2. So this component is 17 ma square omega by 2. This component is 81 ma square omega root 24 by 5. Now vector sum of these will give us L, and they are asking if this L's Z component is so the Z component of this L is 55 ma square omega. That's what they are asking. Okay, so this is angle theta. This is 90 degree to this, so this is 90 minus theta and theta, so this is theta. Okay, so it's cos component minus this thing's sine component, this cos component minus this sine component. Okay, so the cos component of this will be 81 ma square omega root 24 by 5 into root 24 by 5 minus the sine component of this. So L1 is 17 ma square omega by 2 into 1 by 5, that is sine theta. So minus 17 ma square omega by 2 into 5. So clearly I think we can see that this is nowhere near 55 ma square omega. Let's just see. So this will become 10 over here. This is 24 into 25 over here, right? 25 over here, 24 over here. So we'll have ma square omega common. So inside we'll have 81 into 24 upon 25 minus 17 upon 10, right? And this is nowhere near this is nowhere near 55. 81 into 24, right? So this is nowhere near 55. So this option is also wrong. So the two correct options are that the center of mass has about Z has angular velocity omega by 5, and that the angular momentum of this system about the center of mass is 17 ma square omega by 2, right? So I hope you got this solution. It is a bit lengthy because this was a different type of problem in which the axis was tilted, right? So the two angular momentums were like this, going like this and like this. So this was difficult to explain, but when solving, I agree that under paper time pressure this would have been really tough to think about also. So it was best to leave this question in the exam, but this just tells this type of question like helps us understand angular momentum so much in depth, like how this L1 came, this L2 came. So L2 was due to the motion, translatory motion, and L1 was due to the rotation of the discs, right? And the vector sum of 2 will give us the total angular momentum. Its Z component will be this minus of this over here, right? So I hope you guys like the video, and it was like long video, but I really enjoyed this question because somewhat this is like the hardest question of JEE Advanced ever, and I agree it's hard and tough to think in exam times. Okay, so let's not talk more. I'll see you in the next one. I love this question. Thank you. Bye.